Hello again, this is Dr. James Camp from Lee College in Baytown, Texas, and this is part 2 of my lecture on Chapter 5 of Big C++ by K. Horstmann, part 2 of our discussion of functions. Today we're going to be talking about, or in this lecture, we're going to be talking about reusable functions, writing functions so that they can be reused from one program to another, stepwise refinement as a way of defining functions, variable scope and globals, and the use of reference parameters. We're going to leave recursive functions to another class. Okay, so when should you write a function as opposed to just including code in your main program? When you find that you've written nearly identical code over and over and over again, even twice really, it's often worth writing a function to replace the redundant code. Take, for example, this program, which is asking the user to enter the time in hours and minutes. You'll notice that the code written in red is very, very similar. It's not identical. We have hours versus minutes. We have 23 versus 59. But those could be passed as parameters, passed as arguments to a function that essentially does this whole thing and returns the number that you're trying to read. So we could write a function, read int up to. We have a string label that tells the user what they're supposed to enter, and we have an integer parameter that is the high upper limit. We're assuming that the lower limit is always 0. We could write another function, read int between, that took an int low and an int high and allowed us to specify a lower limit other than 0. But you can see that writing this function this way allows that code to be reused between multiple programs. If I have something that isn't doing hours and minutes, but it's doing degrees on a degrees for angles on a triangle, so I want to do between 0 and 90, or if I'm doing temperature degrees, Fahrenheit between 0 and 100, or something like that. I mean, centigrade would be between 0 and 100, otherwise, water wouldn't be water, right? So you can generalize this to a number of different situations, and that's what makes this a reusable function. We can also then see how this makes the main function code so much easier to read. I say int hours equals read int up to hours 23. And that's all I have to write instead of having that huge chunk of code there in my main program. And instead of rewriting the code over and over again, we're practicing code reuse, which is one of those things that good programmers tend to value. Okay, what about this thing we said about stepwise refinement? Stepwise refinement is the job of taking a difficult task and breaking it down into progressively simpler tasks. Okay, and you keep breaking down the simpler tasks into even simpler ones until you're left with tasks that you know how to solve. For example, if you're trying to design a car engine, you wouldn't necessarily know how to go about designing the whole engine, but you can break it down to, well, there's going to be a timing belt somewhere, and I know how to design a belt. If I'm a mechanical engineer, presumably I know how to design a belt. As a computer programmer, I don't know how to design a belt, but that's the idea, is that you can break things down into simpler tasks. And this is often a good way to design functional programs that use functions to break down their tasks into simpler tasks. The book uses the possibly silly example of making coffee, but it's a good example of how human brains go about breaking down tasks. So if I get up in the morning and I want to make coffee, Um, Horstmann apparently likes instant coffee, and so if instant coffee is available, um, they choose to make instant coffee, and if not, they choose to brew coffee. If you have instant coffee available, all you have to do is boil water and then mix the water with the instant coffee. But what if you don't know how to boil water? Well, we can expand that little box into, do you have a microwave? If you do, you can fill a cup with water, put the cup in the microwave and heat for, say, 3 minutes. If not, you can put a pot on the stove and bring it to a boil. So this makes the entire, shows the entire make coffee problem in a stepwise refinement way. Now let's look at a real example with programming. We're going to write a program to take the amount that somebody needs to write for a check. Okay. If you recall, if you've ever written a check, you know that you not only write down the number in digits, but you're supposed to write out the amount that you're paying in English words. Okay. So if I'm paying you $556, I'm supposed to write out 556 in the big blank in the middle of the check. So if we have an electronic bill pay software where you have to, where you, the user, type in an amount, $556, it has to be able to generate the words 556 from the integer that you type. So we're going to write a function to solve this subproblem and call it int name. It's going to return a string, which is, of course, the words that are equivalent to that number. And so, of course, it needs to take a parameter, the number. Now, we're giving a constraint here that we're only going to take numbers less than 1,000 because we're just limiting how complicated this function is going to get. We could go to thousands by just adding a little bit to the complexity of our function, and you'll see that this stepwise refinement process would work just as well if we had thousands. Okay, so let's break it down into smaller steps. If the number is between 1 and 9, then we just need to do some sort of a lookup, if else's or switch case, to generate the words 1 through 9. Okay, and in fact, we're going to do the same thing again for the hundreds because we just say 100, 200, 300, etc. Anytime you need to do something more than once, it's a good idea to turn that task into its own function. So we'll create a function called string digit name that takes a single digit as a parameter and returns the name of that digit. Numbers between 10 and 19 are special cases because they don't follow the rule of like 22, 33, 46. They go 11, 12, 13, 14. You have the teens. So we have a string teen name. We have a function teen name that returns a string, which is the name of a number which is in the teens. For other values between 20 and 99, we're going to have a tens name. So if the number is 23, we're going to return 20 and then figure that the program can look up the number 3 to fill that out. Okay. So here's the pseudocode that we come up with for this. Part is the part of the number that still needs to be converted and it starts out as the whole number. Name is the name of the number that we've generated so far, and it starts as an empty string. Okay. If part is greater than or equal to 100, then we're going to take the name of the hundreds plus the word hundred, and then remove the hundreds from the part. So we're going to %100, send that digit for a name, add 100, and then divide by, we're going to divide by 100 to get the digit, to get the name of the hundreds, and then % by 100 to get rid of the hundreds and keep the rest of it. If part is greater than or equal to 20, we append 10's name and then remove 10's from part. If part is greater than or equal to 10, else if part is greater than or equal to 10. So if it's greater than or equal to 10 but not greater than or equal to 20, we're going to add the teen name, and then we're going to artificially set part to 0 so that we skip the last part where we add the digit name of the last part to the name. Okay. Framing that as pseudocode shows us how to arrange the order of the tests, and it shows how the smaller number gets processed in if statements as we go along. The pseudocode is vague about the actual conversions, and it is very vague about where we need to insert spaces. If you left this with exactly what we put, you'd have something like 274 with no spaces. But we can fix that in the real code. So convert our pseudocode to C++. The last three cases, for some reason they're writing first here. If part greater or equal 20, name is name plus a space, and then 10's name of part, and part equals part %10. Else if part greater or equal 10, name is name plus teen name, part equals 0. You see how this is basically just a direct translation of the pseudocode we just looked at. For the part greater or equal 100, part divided by 100 using integer division is just going to give us a single digit. So we take digit name of that and add 100, and then we leave the remaining part as part %100. Okay. Here's what digit name looks like. Your textbook chose to use a series of ifs. You could just as easily use a switch case setup for this. It's probably how I would have done it. Teen's name, same deal. 10's name. Here you're doing number greater than or equal to, so you have to use ifs and not a switch case. And that's that program. There is a certain cost for writing a function. You need to design code and test it. The function needs to be documented if you're doing this for real in the real working world. You need to spend some effort to make the function reusable rather than just an exact copy of the code you'd write for that particular context. The difference between hard coding between 0 and 60 and having a parameter of the lower and upper limits, for example. So it's tempting to write long functions because it's just hard to write extra functions. But as a rule of thumb, a function that's too long to fit on a single screen should be broken up into smaller functions. And when you get to your course, your first course project for this semester, which is going to be a functional program, a program that you're going to break into lots of functions, I want you to follow this rule of thumb. I don't want functions that are several pages long. I want you to start thinking about how you can break things up into smaller and smaller reusable bits. I also don't want you to write lots and lots of little functions that do exactly one thing. For example, if we're simulating a database software and we write a little function that pretends to write to the database, you're not going to write several different functions that write different things to the database. You're going to have one database write function that takes parameters that tell it what it's supposed to write. And that's a good segue into a brief discussion of what we call stub functions. When you're writing a larger program and you know you're going to have lots of smaller functions that add up to a bigger program, don't try to write and test all of your functions at once, because something's going to break and it's going to be very difficult to figure out which thing is broken. The best thing to do is to write the functions that you don't know how to write yet, or that you haven't written yet, whether you know how to write them or not, as what we call stubs. And a stub is a function that might return a simple value sufficient for testing another function, like it might always return the number 1 if you're looking for an integer, or it might always return a string that just says, here's my string, or something like that. And then it might write a debug message on the screen to help you see the order of function execution. Now executing function X, or in my previous example where we were writing to a database, but we don't know database coding yet in this class, you might just write a debug message to the screen that says writing to database, : and then you say what information you're writing to the database. And that would be a stub function. Examples of stub functions from the program we just immediately wrote, the digit name, tens name thing. A digit 1, 2, 3, 4, 5 maybe sounds a little like mumble, or that's what they're going to go with here. A tens 20, 30, 40, 50 sounds like mumble T. So if you write these simple things and say, well, I don't know how to write a digit name or a tens name yet, but I'll figure that out later, then when you compile the code and run it, you get 274 gets broken into mumble 100 mumbledy mumble, which sounds silly, but it shows that the basic logic of the function is working correctly. And now you go through and you unstubify one of those stub functions. You fix the digit name, and then you'll get 200 mumbledy 4. Okay, and then you go through and you fix the tens name, and you'll get 274. Okay, so you unstubify one thing at a time. Finally, when you design a complex set of functions, it's a good idea to manually walk through them, especially if the computer is not generating the output you think you should be getting. Okay, this process is called tracing your code. And what you do is you trace each function separately. You maybe get a set of index cards, one for each function, and you say, okay, for the int name function, I've got two variables, part and name, and so I'm going to start with part equals the whole number and name equals an empty string, and then after the first pass, we've taken the 4 off of part, so it's now 16, and we passed that 4 to digit name plus 100, so we get 400 for name. Okay, and we'd continue that through tracing the rest of that function. If digit name is a particularly complicated function, you might add another sheet of paper or another index card to trace that function call, and before long your work table might be covered with index cards, but it's a good way to trace through your code. Okay, so moving again now back from advice on how to write functions back to some technical aspects of functions. You can only have one main function, but you can have as many variables and parameters spread amongst as many functions as you need. Okay. Can different variables have the same name in different functions? Yes. Okay. It's kind of bad style to do so on purpose, but C++ won't punish you for doing so. And the reason is that each variable has something called a scope. The scope of a variable is the part of your program in which we say that that variable is visible. Okay, a variable is visible from the point at which it's defined until the end of the code block it was defined in. You can think of a code block as any of those things that are surrounded by curly braces. Okay, a function body, an if-else chunk, a loop body. Okay. Variables defined inside one code block cannot be seen outside that code block. So if I define a variable inside main, it can't be seen by my function. If I define it inside a function, it can't be seen in main. Okay. Because scopes do not overlap, a name in one scope is not going to conflict with a name in another scope. Okay. But what if a name is defined in main, and then I create a loop, a while loop, and I redefine another variable with the same name? Well, the inner variable is said to shadow the outer variable. You can't see the outer variable anymore because the inner variable takes precedence. Here's an example of variable scope between two different blocks. Okay. Cube volume, the function, has a double volume and a return, and it returns volume. Okay, so there's a red volume, and then int main, they also declared a variable called volume, which they set to cube volume of 2 plus 2. Okay, why the plus 2? Just to show that these two volumes are not going to be equal just because they have the same name. Okay. The red volume is going to have value 8. The purple volume is going to have value 10. Okay. They're each in scope in a different function. And in fact, as soon as cube volume ceases, finishes executing and returns, the red volume ceases to exist, and only the purple volume now exists. Here's an example of scope with an inner and outer scope. Okay, the red count is the outer scope. It exists through the entire main function, but as soon as we enter the for loop and we define a new count variable, the purple count shadows the red count, so we can only see the purple count in here. Okay, so for the duration of the for loop, count starts at 0, it adds 5 at a time. It goes to less than n minus 5. Well, n is 40, so it goes to less than 35, so it stops at 30. And then we immediately switch back to the red count, which has never changed. It's been 40 the whole time. Okay, so what would the output of this program be? We'd count 0, 5, 10, 15, 20, 25, 30. Then we'd exit the for loop, and count suddenly becomes 40 again, and we'd output 40. Okay. A variable defined inside a code block is local to that block and ceases to exist outside that block. So the I in this case, you can see out I as long as you're inside the for loop, but as soon as you exit the for loop, if you try to see out I, you'd get an error, which, the error would be something like unidentified or unknown identifier, no variable of that name in this scope. Another scope error is it's illegal to define two variables with the same name in the same scope. Okay, notice that we have a parameter variable named volume. That's the green one. So the purple volume is an error because you can't define a non-parameter variable to have the same name as a parameter variable. The red volume is an error because even if line 1 was okay, we've just defined a volume. We can't define another volume in the same scope. You can define another variable with the same name in a nested block. It's just not recommended. This code is confusing and it's highly discouraged. Pick a different name for either the parameter or for the variable inside the if statement. Um, there's also something called a global variable. Global variables have scope that covers the entire program. Some programming languages have global variables, some like C# and Java do not. Global variables are kind of a controversial issue in computer science because while they can be seen by all functions, and that limits how many variables you have to keep passing back and forth between functions, it becomes tricky to debug because you have to track which function is changing that variable at the same time. Let's say you call one function that adds 5 to the global variable and then another function that subtracts 5 from it. Maybe you didn't mean to have that circular logic and get the global variable right back to where it started from, but that's what happened. Some situations do require global variables, though, such as a shared time of day clock in a control system for, say, your thermostat or something like that. Or there are also very good, globals are also very useful for constants. If you're writing a banking app and there are certain overdraw penalties that should be constant no matter what operation you're doing, then those could be declared as global constants. Here's an example of using a global variable. We call withdraw of 1,000. The withdraw function changes the global balance. Since there's only one function that works on the global balance, that's not too bad. But what if we were writing a real banking program and we had 15 different functions that might operate on the balance, and they might be used by different numbers of, they might be written by different programmers. It might be difficult to track which function is doing what to balance at which time. A better way to do this is to pass balance along with amount to withdraw and return the new balance. So balance equals withdraw of balance comma 1,000. And now we've eliminated the global variable, and we know that we kind of have to give permission to each function to change balance as we go. An example of a really stupid program using a global variable here is we have a program contribute, a function contribute, which if f does not equal 0, p equals p times f, and then we return p, but we've actually changed global variable p in the process of running contribute, so it becomes very difficult to track what happened to p and what happened to n in tracing through this program. However, there are situations where you need to do something like this, especially if you ever get into threading, multi-threaded programs. Often the different threads need to work on a single global variable, and so there are situations where you have to deal with that. And as you get into your more advanced computer science classes, you'll learn about how to manage global variables so that you don't have this who did what to who problem. Okay, another solution to the global variable problem is to use reference parameters. Okay, suppose you would like a function to get the user's last name and ID number. Okay, the variables for this data are in the main function scope, but you want the function to change them for you or to set them for you. You use a reference parameter to do that. So if I say withdraw Harry's account 100, and I want the program to actually change the balance of Harry's account, what I need to do, well, if I write this the way we've learned to write functions so far, this doesn't work because the function can't modify the balance. It doesn't have permission to modify what, it's not permission. The problem is that balance is a value parameter. Okay. All function parameters are by default. That means we make a copy of the main program's variable and assign it to the variable balance. So balance equals 1000 because it's a copy of Harry's account. Balance changes to 900, but then as soon as the function returns, balance disappears and Harry's account is still 1000. The solution to this is a reference parameter. Okay, a reference parameter is actually, instead of copying the variable, it's passing the memory address, the memory location of a variable. We indicate a reference parameter by putting an ampersand after the type name. Okay, so void withdraw double ampersand balance means that we're passing a reference to a variable and we're calling that reference balance. Okay, so if I write this code, if balance greater than equal to amount, balance equals balance minus amount, else balance equals balance minus penalty. Okay, note here I used a global constant for penalty. This is one of those situations where globals make sense, is that we probably want the penalty amount to be consistent across different functions, so we can make that a constant, a global constant. Because it's constant, you don't have to worry about which functions might be changing it at any given time, so it makes perfect sense to declare that as a global. So if we write this code, what happens is when we call withdraw Harry's account 100, balance is now set as a reference to Harry's account. And when we say balance equals balance minus amount, we actually change Harry's account by reference. And then after the function call, when balance and amount go away, Harry's account has been set to 900. Okay. We can't say withdraw 1000, 500. 1000 isn't a variable, it's a literal number, and literal numbers in C++ do not have a memory address. So we can't change the number literal. For the same reason, you can't supply a expression, withdraw Harry's account plus 150. We'd have to add 150 to Harry's account and then call the withdraw function. Okay, now why not, if we can use these reference parameters to change variables back in the calling function, why not write cube volume, double side length, double reference volume? The answer is that then we lose some convenience. We can't say cout cube volume of 2 or volume equals cube volume of 2. Okay. But sometimes we do want to return more than one value. And as you recall, return value, the return statement in C++ can only return one value. So if the caller wants more than 2 values, the only way to do this is to use reference parameters, one for each value that you want to return. So void powers, parens double x, double reference square, double reference cube, and then you calculate square, and then you calculate cube. And that's going to set the value of those variables that were passed as references. Reference parameters are also very handy because when we start passing large objects, strings, vectors, structs, and objects that we'll get to in future lectures, copying that whole object into a parameter variable costs computer time and memory. It's less efficient. Using a reference parameter, you're just passing the address, the memory location of the variable, and so it's much faster and more efficient. But what if you don't want them to change the original value? Well, you can pass something as a constant reference. You just add the const keyword to the parameter, and so const string reference str will prevent you from accidentally changing the value of str in that function. Okay, and that brings us to the end of part 2 of our lesson on functions and functional programming. It's time to do a little bit of function practice. The assignment I have in mind for the more advanced programming here is write a program that tracks your bank balance. Okay, do it as a local scope variable in main, so no cheating with global variables here. Okay, start with a balance of, say, $1,000. Write deposit funds and withdraw funds functions that take the balance as a reference parameter. Okay, so you're going to change the balance in the function, and it's going to reference that back to the main function. If insufficient funds for withdrawal, charge a $25 fee. Okay, let the user type D to deposit or W to withdraw, and then type an amount. Okay, and then call whichever of your functions is appropriate and print the new balance to the screen. Not a very difficult program, but a little more advanced perhaps than the practice programs we've done before. So put your best effort into it, and I look forward to seeing what you come up with. Until next time, good luck and happy programming.